Good afternoon, JFall. I'm sure everybody had a great lunch. Is everybody feeling energized after this tight voting experience or what? Yeah? Nice. I couldn't vote, by the way. It didn't work, but anyway. Speaking of lunch, I want to tell you a small story. 20-something years ago, I was working on my first real software development job. And by real, I mean that it was a job building a desktop application for a small company that actually had quite a nice market share in its domain. Its domain was card printing software. You know, those plastic things you carry in your wallet, the loyalty, credit cards, corporate IDs, that kind of stuff. And all of this happened in a small fisherman's village located like 40-something kilometers north of Lisbon, which is a great location during summer to go and still have a swim after work, except when you need to be busy solving some issues in the interface between your application and the printer that actually produces the cards. And as the years went by and printers got more and more complicated, this would happen more often. Now, my point here is that software is definitely not perfect. There are failures that can happen at any time. In fact, I just told you I could not vote because, well, reasons. There's radio communication down here is not working as it should. And that's also the reason why cloud providers announce their availability not in terms of 100%, but in terms of how close they can get to 100%. If you see a cloud provider talking about 99.999% availability, that's already pretty good. From 20-something years ago, on a completely different market with a completely different technology, to nowadays, 100% is, if I may say so, the holy grail of software reliability engineering. It's something that I believe will just not be possible at all to achieve. And why is that, you may ask? Well, let's take a look at something as simple as crossing the street. When I am preparing to cross the street, lots of things can go wrong. I may just step on some dog poo, or I can trip on a stone, or I may be hit by a car who didn't notice I was coming, or in a city like Amsterdam, for example, it's more likely I'll be hit by a delivery guy on a bike. And if we look at today's landscape of microservices with counts of instances that can easily go into the thousands in heterogeneous IT landscapes, big data centers, there are just too many things that can fail. You can have crash failures, timing failures, communication failures. Services can behave unexpectedly, and that happens so often that they even created a term for that. That's a Byzantine failure. The number of things that can go wrong is just so big that it is humanly impossible to try to comprehend and build solutions for all of them at the same time. Which is why I propose that we focus today on one issue: communication. And who is, do you think, the better and also the worst communicator at the face of this earth? It's people. Because when we communicate, especially towards one another, we use both verbal and non-verbal communication. Verbal is easy, non-verbal is, well, not so easy for many people. On top of that, we often assume things. We believe that the other person not only is understanding what we are saying, but also that they already have some sort of pre-existing knowledge. And this goes both ways. The end result is that 2 months down the line, after two teams have met to discuss some sort of API, they try to get the services to talk and they don't. And someone utters the famous words, "Oh yeah, by the way, I forgot to tell you that." Now, there are, of course, many ways that can be proposed to solve this, or at least to help it. There are a number of tools and techniques available that can help you do this. And today I propose that we look at the problem and try to compare it with something that we all know, or at least most of us do, which is the way how a programming language works. Now, when you are using a programming language, there are a set of tools that go from what you type, that text that is kind of human readable, into something that the machine itself can execute. And it so happens that in most programming language, the very first step is to compile what you have written into something that the machine can begin to make sense of. That step is, you may be wondering, yeah, how do you apply that to API and service development? Well, I suggest that the best way to avoid misunderstandings on an initial stage is to actually have squads using a predefined, with a well-defined syntax specifications document. They use that document to communicate with each other. They enrich it and make it as complete as possible. And when they get to the point where that document is as complete as possible, then we can kind of compile it into code. And then we are sure that we have a foundation to build upon that respects the letter of the specification. Now, this is, of course, iterative. Many iterations are required during the lifetime of a service, and this can happen over and over and over again, and you always have the guarantee that your foundation respects the letter of the specification. In many programming languages, the next step is the assembly step. Now, looking at languages such as C and C++, this means that the result of the previous step is going to be assembled. So usually it's assembly language, it goes into machine instructions, never mind. Because what I like is the other definition of assembly. The other definition of assembly is that we bring manufactured parts together to build a machine or some other manufactured element. Looking at APIs and services, well, let's just bring them together. And how do we bring them together? All right. Every time you have an API, you have some service that uses that API, is consuming it, and you have some other service that is providing services through that API. Therefore, the team developing the consumer service provides a contract. Now, this is called consumer-driven contract testing, and it is in no way different from what we do when we go to the cafe, we approach the person behind the counter and says, "I'll have a latte, please." You already know what to expect. If that person brings you an Americano, then you look at it and say, "Yep, sorry, that's not what I ordered." Likewise, with consumer-driven contract testing, the consumer produces a contract, which is nothing else than a text file using some syntax, that expresses the intent and, more importantly, the expectations of the consumer with regards to the API that the producer exposes. And then the consumer uses this contract for its own development and for its own tests. The producer, on its hand, uses this contract to test itself. When the producer is able to respond to the requests made to its API that according to the consumer's contract, then they know that they fulfill the intent, and the specification of each consumer. This whole thing is called consumer-driven contract testing, as I have said, and it adds another layer of assurance to the relationship between these services. So previously, we generated code to respect the letter of the specification, and now we have a way to respect the spirit of the specification. On top of this, people can also use a toll gate called Can I Deploy? Now, of course, if tests are passing on both sides, then that means the services are compatible, and they can be moved on to whatever environment is next. If tests are failing, then there is some sort of incompatibility there, and if we put these services live, whatever it is that they provide is just not going to work. So we don't deploy. That's the purpose of this toll gate. Now, back to programming languages. We have something that the machine can interpret, but it still needs to run on its final destination. We see this phenomenon happening with the JVM as well. So let's imagine we compiled an application, everything works perfectly, all tests passed, everything is green, is beautiful, we create a container, we spin it up, it launches the application, and we get a class not found exception, or even worse, a method not found exception. What does that mean? It means that one of the dependencies is not there, because the JVM is using a mechanism called runtime dynamic linking. How can we transfer this concept to services and APIs? Well, the suggestion is to use staging environments. With a staging environment is something that is as close as the real live environment, production, but it's not live. We don't have real customers there. What's the idea? All right, in the continuous integration and continuous deployment environments, we have executed our unit tests, we have executed our module tests, bigger integration tests, contract tests, but that only verifies that what we have under our direct control works. And what about everything else? I'm thinking Kubernetes configurations. I'm thinking container memory limits. Okay, we are talking about services, so there's probably some sort of service discovery mechanism in place. Do our services interact with the service discovery mechanism correctly? They are probably located in different data centers, so do firewalls need to be changed? Is there any networking setting that needs to be tweaked? That's what staging environments are good for. Everybody deploys there, and then you run 1 or 2 integration tests there. And before someone starts throwing tomatoes at me, I don't mean that you run your entire suite of all detailed integration tests with every single possible combination that could possibly go wrong. No, you just run 1 or 2 tests, as long as they exercise the critical paths that give you confidence that the service is correctly configured to run in that environment. That's sufficient. Okay. Now, we already executed lots of things in CI/CD. We have the service running in staging, and now it comes to production. And our service is quite important. So what can we do to cater for the possibility that even those small things that may have gone through all those tests show up in production? Well, we can use something called canary deployments. Now, I'm not sure if you are familiar with the term, so I'm going to tell you another little story. Back in 1911, the usage of coal mines was in full swing. And coal mines have a couple of characteristics. First of all, especially in the early 20th century, the industry revolution in full swing, more and more energy being used, more and more was being dug, so they got really deep. And with deep mines, there's a ventilation problem. And also the very nature of coal mines makes them susceptible to, well, dangerous gases and environments that are just not suitable to support human life. In other words, miners would eventually die down there. A researcher came with an idea. Let's use canneries as a way of telling whether the environment in the mine is sound. Now, a cannery, literally that small yellow bird, they would take canneries inside special cages down the mine, and the miners would always keep an ear on the cannery, and if the cannery went silent for too long, or worse, if it was found unconscious in the bottom of the cage, then that was a pretty good sign that they had to get out of there as soon as possible. Things were getting dangerous. We can apply the same principle to any production deployment. And the way how it works is that we just leave whatever existing instances of the service are there, and we replace them with a cannery, which is a single instance of the new service version, and we look at it very carefully. It receives a small percentage of traffic. And we ask questions, all right, are there errors? Is it working? Does it look good? If the answer is yes, then we just replace the other instances, everything is fine, the sun is shining, and we go for drinks. Otherwise, we roll back this single instance, and because whatever it was that was happening only affected a small percentage of traffic, it means that also the impact on customers is limited to a very high degree. When people choose to combine all of these techniques, they have a greater degree of assurance. Now, during build time and staging, in continuous integration and continuous deployment environments, build. We can produce code from specification. We can use contract-based testing. All of this in CI/CD. Then staging environments can be touched if the contract tests are green to ensure that configurations are correct. And then finally, cannery deployments can be used in production. The whole point from generating code from specifications to verifying contracts and exercising these services is to ensure that whatever it was that people have negotiated and refined at the beginning of the development stage works when the services actually reach a live environment. And this takes me back again, because would it today, in that little fisherman's village, and had these measures been in place, well, back then it was a desktop application and a printer. Were it today, it would probably be a set of services in the cloud, doing image processing, probably transferring data. But for sure, that the combination of these techniques would have allowed me to spend more time on that beach instead of being in front of a computer screen getting even more gray hair. These are the techniques we have available for our squads to improve the way how their services speak to each other, and hopefully also to improve the way how they themselves talk to each other. I hope I have inspired you to use these or any other techniques to improve the way how your services talk, reduce the amount of communication errors, and, well, just have more time for drinks at the end of the day. In the meantime, if you want to discuss something, I will be around. We'll drop by in some breaks at the ING booth. And if you want to learn a bit more about Kafka's usage at ING. My colleague Team will be discussing that same matter on room 1 right after this. Thank you so much, and have a great JFall.